Okay, test. Alt P.
Hi, it's Mrs. Wig here, and we are doing section 8.2, the Pythagorean Theorem and its converse. So by the end of this lesson, you'll be able to find the missing side length of right triangles using the Pythagorean Theorem and also identify right triangles by using its converse. So this should be a review for most of you, but we will go over it anyways. The Pythagorean Theorem in words is when you have a right triangle, the sum of the squares of the lengths of the legs, so side BC or small a and side CA or small b, squared is equal to the length of the hypotenuse squared. So in symbols, we can see that is a squared plus b squared equals c squared. So let's do some review problems here. So the first one here, A, we have side or leg length of 6, leg length of 15, and our hypotenuse length of x. So that means that x is our c. So when we use the Pythagorean theorem, we can plug in 6 squared plus 15 squared equals x squared. After solving using our calculator, we find that 6 squared plus 15 squared equals 261. And then, of course, we need to take the square root of both sides, and we get x is equal to the square root of 261, which also can be simplified into 3 square root of 29. So the next problem, now we are given the hypotenuse, we are given c squared, and we're trying to find a squared. So when we set up our equation, we're going to use x as a squared. So x squared plus 9 squared is equal to 11 squared. Simplifying farther, we get x squared plus 81 equals 121. Subtract 81 from both sides, and we get x squared is equal to 40. Square root both sides. X is equal to the square root of 40, or we can reduce it to 2 square root of 10. So the next concept, which should be new for most of you, is a Pythagorean triple. And a Pythagorean triple is a set of 3 numbers that are whole numbers, so no decimals, no fractions, such that when you apply the Pythagorean theorem, a squared plus b squared, you get c squared of a whole number. So you may have ran into these before, and one really common one is 3, 4, and 5. Because we know if we take 3 squared, which is 9, plus 4 squared, 16, we get 25, which is also 5 squared. So here's just a list of some common Pythagorean triples. We have 3, 4, and 5, 5, 12, and 13, 8, 15, and 17, and 7, 24, and 25. So underneath these sets of 3 numbers, we also can have common multiples given a common factor 2. We see that 6, 8, and 10 will also be a Pythagorean triple when setting up right triangles. And here's a set. So, an example, use the Pythagorean triples to find x and explain your reasoning. So we're looking at this right triangle right here. We see we have 12 on one leg, 15 for the hypotenuse because the hypotenuse is opposite of the 90-degree angle, and we have x. So we can notice that 15 and 12 are both multiples of 3. So we have 12 divided by 3 is 4, 15 divided by 3 is 5. So we have the start of our 3, 4, 5 triangle. So we can see that 3 times 3, or 9, is going to be our missing side. And if you wanted to check this with the Pythagorean theorem, it is going to check out. So the next one we have might be a little more difficult to recognize. We have a leg length of 14, a hypotenuse of 50, and a leg length of x. So what I'm going to do is I'm going to say, okay, 14 and 50. Let's go back to that list of triples, common triples. Do I see any that have a common factor of 7 for one number and 50? Do any have factors of those two numbers. And it looks like this set, 7 is a factor of 14 and 25 is a factor of 50. And they're both, if we multiply by 2, we get the answer. So let's see if that helps us here. So A equals 14 and C equals 50. We take 7 times 2, 25 times 2. So we know, if we look back here, that 24 is our missing number of our triple. So we can take 24 times 2 is equal to 48. And if we plug that in here and use the Pythagorean theorem, we can check our answer, and it will check out. So take a look at this problem. We'll give you a couple seconds to see if you can figure out the answer using those common triples. We have a side of 12 feet high, and the ladder is 5 feet from the house. So let's take a look back, 5 and 12. It looks like the length of the ladder is going to be 13. So we can check our answer here using the Pythagorean theorem. 25 plus 144 is equal to c squared. 169 is equal to c squared, so we know c is equal to 13. And we can circle C for our answer. The next theorem that is presented in this section is the converse of Pythagorean theorem. So we know already that if we have a right triangle, that if we square the two sides, it'll equal the square of the hypotenuse. But we can also say the opposite, that if we have a triangle where one side squared plus the other side squared is equal to the third side squared, then we absolutely know that that triangle is a right triangle. The next piece is we can take those sums of the a squared plus b squared and compare it to the c squared for our non-right triangles and figure out whether or not that triangle is acute or obtuse. So theorem 8.6 says that if a square of the length of the longest side, or c squared, is less than the sum of the squares of the other two sides, so if c squared is less than a squared plus b squared, then we know that the triangle is acute, which means that all of the angles are less than 90 degrees. If the square of the length of the longest side, so our c squared, is greater than a squared plus b squared, then we know that the triangle is obtuse, meaning that it has an angle of greater than 90 degrees. So we can see here that that's our angle C is greater than 90 degrees, and back on the first part of the theorem, that all of these angles are less than 90 degrees. So let's check this out. It says determine whether each set of numbers can be measures of the sides of a triangle. If they can, classify your triangle as acute, obtuse, or right. So we have 15, 36, and 39. We're going to set up our equation a squared plus b squared, and we're not sure about this. Is it equal to, is it greater than, is it less than 39 squared? So after doing some work on the calculator, we see 225 plus 1,296 is going to be less than, equal to, or greater than 1521. And a little bit of math, we see that actually they are equal, so we know that this will be a right triangle. Let's try one more. So determine whether the set of numbers can be the measures of a triangle. So I just set up a little drawing here to help myself visualize. And I want to know, is this going to be acute, obtuse, or right? And it might appear as acute right now, but I'm not 100% sure, so I need to use the math to prove it. So I set up 16 squared plus 18 squared equals, maybe, we're not sure, 26 squared. So after doing our math, we see that 580, which is the total of our a squared plus b squared, is less than 676, which is the total of our c squared. So if we go back to look at those theorems, our c squared is greater than our a squared plus b squared. So we have this right here, which means it's actually an obtuse triangle. So even though I drew my drawing as acute, it's actually obtuse. So that is the end of 8.2, and we will see you in class tomorrow.